Good afternoon, everyone, and thank you very much for your attention. My name is Ildefonso de la Cruz. I am the principal analyst at Omdia, focusing on the market research for mission critical communications. Today, I have the pleasure to chair this panel, and I have with me three experts that are going to talk about the challenges of the planning of future mission critical networks. I think we've come a long way from questioning whether there's going to be an evolution. Right now, we are asking the right questions. When is it going to happen? How do we make it efficient? So to start, I have with me Anthony Sutton, Chief Commercial Officer at Ramplin Wireless. He has 25 years of experience, started as an engineer, but quickly crossed to the dark side, and now is focusing on the business development and sales, and he has extensive experience in adopting solutions according to the diverse needs of his customers. Anthony?
So good afternoon, everybody. Thank you very much for coming along. So what I'll do is I want to sort of try and set the stage a little bit about the topic of this conversation. But I'll first of all just do a very, very quick high-level sort of chat about who Ramplan are, just so that you understand who we are. So as a company, we've been around really for about 8-9 years now. The main focus of our business is developing and evolving how people use software to plan radio systems. And you'll understand a little bit in a minute about how relevant that is to the discussion topics today. So if we look at sort of some of the aspects that we're looking at trying to overcome today is really how we can look at sort of what outdoor signals are, indoor signals, but primarily how radio systems are actually affected by each other. So outdoor and indoor, indoor and outdoor. So, as I say, there's really two questions I wanted to sort of bring up, and I'll talk a little bit about those. Hopefully, it'll stimulate some conversations with you is, what type of coverage do I get from my Tetra network, and how can I compare that to my LTE network, whether I'm building my own LTE network or whether I'm going to use an outsourced LTE network. And the second one is really when you're looking more in an in-building environment, how we can actually look and compare to ensure that the LTE systems have very similar or ideally identical coverage footprints to the push-to-talk systems, be it Tetra, DMR, or P25. So let's look about the old first, new versus old. So in reality, what do we want to do? We want to understand what the current coverage is, both outside and inside our building environments. We want to understand where I'm going to have gaps between my old system and my new system. And, what will our LTE network look like? Where are those base station sites going to be, both outside? What coverage have I got in the inside environment? And also, as I said, how do you analyze what you've got in both aspects? So in reality, we're looking at a combination of pulling outdoor sites into an in-building environment. So I'm not going to spend too much time looking at the slides, but you can get a feel for what's going on. So here we've got an outdoor environment, looking at a building, also looking at how we can analyze sort of small cells, because that's how a lot of the LTE coverage that we're going to see will be delivered. But then what we also need to look at is how you can compare the two networks. And that's going to be essential no matter whether you're building your own network or if you're using an operator-led network, not just from a downlink point of view, but also understanding whether you can get sufficient uplink power back from your push-to-talk radio system, or actually if you're going to get enough throughput back from your LTE systems themselves. And then the second part is really looking at the in-building solutions that are going to be out there. How do we actually go out and actually do designs? Are you going to go out and do the conventional way of setting up test transmitters, walking around and try and do testing itself? Are you going to do a walk test looking at the existing network coverage, or are you going to use a combination of those to bring in different types of solutions? So when you're using tools, there's a lot of things that you can do that allow you to compare the existing networks to each other and then do that analytical comparison of the Tetra to the LTE or Tetra to 5G, so you can really see what's going on. And there's lots of different things you can do, so looking at the floor plans, and we know that if we understand how people are using Tetra networks, they're using them in lots of areas where commercial operators don't necessarily deploy systems. So the back of house, the emergency escapes, they're places where Tetra networks need to be operational, but a traditional operator LTE system or 5G system would not have been designed to deliver that. So you want to be able to look at and understand where those differences are when you compare what you've got to what you're expecting to get, and then work out how you would actually go away and actually improve the network connectivity that you've got. So that's my little introduction on what we are, and if you want to come and have a chat to me after, please do.
Let me see first if we have any questions from the audience for Anthony. If not, we'll have a chance to aggregate all the questions right after the presentations. But if there are any pressing questions nobody wants to put Anthony on the spot, then I might give him a hard time and tell him, in your experience with real deployments, depending on large deployments, small deployments, the combination of indoor and outdoor, what is the most common challenge when it comes to the coverage? Is it based on the pure physics, the fact that LMR technology transmits in much lower frequency spectrum, or are there other challenges involved in the adoption of broadband technology?
Yeah, so I'd say you've got a combination of all of those, really. The frequency for LMR being lower, you get much more coverage from the base station itself, not only in the outdoor environment, but also in the indoor environment. But when you're voice-centric, you're actually working at different signal levels to having a database system. And especially if you want to achieve high data rates, you've got to have a much better quality of signal in the building itself. I mean, a prime example is having spoken to a nationwide organization who are going through this process of evolving from a Tetra system to also having LTE, where they're concerned they have upwards of 30,000 buildings that may actually require additional coverage. And their challenge is they just don't know, because they're concerned about the different frequency and the different penetrations that come along with that. And it's a lot of time and effort to go and walk test 30,000 buildings. So trying to find other ways that enable people to deliver that and understand and mitigate their risks as well.
Absolutely. Next, we have Tom Cooper, Senior Sales Director at Avari Wireless. With more than 35 years of experience, he's focused these last 25 on the in-building covering challenges. And today, he's here to present what are the challenges that come from adopting broadband and what is the impact on indoor coverage.
Thank you, Ildefonso. I'm also going to talk about existing challenges with narrowband technologies, because that's what we have today. So it's only going to get worse tomorrow. So we'll talk about solutions, the types of technologies that are used to fulfill the design tool examples that Anthony just mentioned. So little quickly background on our company. We're a North American manufacturer. We provide distributed antenna system, active electronic components for DAS, for emergency responder applications, including Tetra as well as broadband. I guess a real key thing to emphasize here, given the nature we're talking mission critical equipment here. We're not just looking at putting a BDA, a bidirectional amplifier, in a building and introducing the weakest link to the coverage, reliability, et cetera. So we're looking at purpose-built equipment designed for mission-critical applications. And another key aspect is we'll be talking about digital. You keep hearing the word digital in today's world. You can't open your email any day without seeing 5G and things like that. It's a cliche, but everything is going digital. So we'll look a little bit at what some of the practical benefits and advantages that digital transport can do. As far as looking at types of deployments, we really specialize. We love to do 30,000 buildings, as Anthony just mentioned, but not all of the buildings need a very advanced system. Different tools are required for different applications. It is truly a toolbox analogy. If you've got a large, very demanding, complex application, it's important to not only have the right tool, but have something that's designed for high system availability, et cetera. So looking at buildings like what we're in, convention centers, hospitals, shopping malls, enterprise buildings, subway, metro systems, airports, et cetera. All these areas have one thing in common, obviously, is they block the outdoor radio system, and people need to communicate indoors. It goes without saying. Again, we're a North American team, and we operate globally. So what are examples of some of these larger facilities? So that's what this slide illustrates. You've got stadiums, sports facilities, concert halls, downtown areas, sky-rise, Class A real estate buildings, campuses. They can be educational campuses, universities with dozens of buildings, sometimes hundreds of buildings. You need a proper integrated radio network to communicate from the indoors to the outdoors and have a responder in the basement of one building talking seamlessly to the responder in the basement of an adjoining building, et cetera. Much of today's life goes on indoors. Below ground facilities can include subway tunnels, specialized applications as well. Nowadays, many people order things online, so this has created a whole new kind of DAS requirement. Large, multiple million square foot warehouses. We've done facilities in private airports. Every time somebody orders something online, it goes through these types of facilities. As the world keeps changing, more applications are defined. So let's look at what some of the challenges are in these large, complex facilities. So just consider this as a map of downtown anywhere. And what you often have throughout the world is on the top of each of these buildings, you might have a directional pickup antenna pointing towards a donor site. And all of these buildings with antenna systems crisscrossing one another using coaxial BDAs, et cetera. Obviously, that's a recipe for noise, interference, et cetera. It's really becoming a large understanding in the industry, as well as the need for system reliability. So just size, distances, sending signals, long distances, tens of kilometers, for example, in metro systems. Also challenges related to fiber availability, flexibility of design. You need fiber. What if you don't have, for example, single mode fiber? Well, we can use multi-mode fiber, things like that, and how you can really create a proper network using a relevant distribution architecture. Multiple services, content aggregation. What that speaks to is combining content, either from different bands or from different radio sources. They can be a direct connect to a base station on site, belong to a building like this, or one of the buildings shown here, maintenance, security operations, private mobile radio, combined with off-air local responder and multiple bands. We can aggregate the content digitally, and we can send it out as combined data, multiple bands, deliver it, steer it to different locations within a facility, et cetera. Reliability and redundancy is extremely important. Again, we're talking mission critical applications, 5 nines availability. You need systems that eliminate single points of failure. So I'll show you an illustration of a redundant system, purpose built for high availability, excuse me, mission critical applications. Scalability speaks to 2 elements really, the requirement to expand the system in the future to other facilities, other buildings sometimes, as well as add new bands. So for example, 380 and 170 today, Tetra systems, and what if you need to add 800, 900 LTE later without needing to replace the complete network? When we use the word digital, mostly what we're talking about here is the digital transport over the fiber. So this slide illustrates the difference between traditional analog fiber DAS. So essentially what you're doing with the analog system, the master head-end unit, really what you're doing is you're modulating a laser at RF. You're turning a light source on and off at 380 million times per second. You're sending it as a pulse of light through the fiber. You have a laser detector at the other end, converts it back to RF, and then you amplify it and distribute it, etc. It works fine to the extent in which it works. What we do differently with digital DAS is before we convert the RF signal to light, we actually convert it to packet data, and we send it as digital content through the fiber. And there's a lot of advantages for that. And again, you can go much greater distances if you plug in a higher power SFP plug-in unit. The bands don't interfere. There's different, higher fidelity, higher performance, better signal to noise, less impact on the donor sites, etc. So when we're talking digital here, we're talking about the transmission of the radio system content through the fiber. Really quickly, the redundancy operation I mentioned earlier. If you look at the remote unit shown on the right, fiber-fed BDA, whatever you want to call it, key differentiator here is it has 2 fiber interfaces, so it is connected to 2 different head-end sources through different diverse fiber paths. What's shown here is a primary site which has direct connection through a base station backed up with an off-air repeater coming in. It doesn't really matter. They can both be off-air. They can both be direct connect. The bottom line is the remote unit has the intelligence to realize that something has happened upstream. Somebody's cut the fiber, maybe a lightning strike at the head end or fire in the equipment room or something has happened. So the system will revert operation to the secondary path and the system will stay operational. Handover just takes a few seconds. This shows a more complex architecture. Sometimes can spend over 30 minutes talking about this. I promise I won't. What this shows is 2 primary head-end feeds. We talked earlier about a relevant network distribution architecture. What you see in the middle of the screen is a secondary layer. So we're going from 2 independent head-end sites out to 2, again, spatially separated, independent secondary head-end sites, and then going out to remote units. So this is a very, very simplified rendition of an actual deployment, which has close to 100 remote units now, multiple bands going through it. This is capable of up to 4 different RF bands. And again, we can deliver the content individually on an as-required basis throughout the campus facility. This last slide shows similar type of thing. This is a university type of design with 2 head ends. In this case, you can see there's 7 what we call secondary head ends. This really speaks to the fact of, again, fiber limitations. Often you've got a situation where everything is connected to something, but not everything is connected to the same thing. So this allows you to make most efficient use of existing fiber plant limitations, as well as provide an end-to-end redundant system in multiple bands, et cetera. So this is very simplified, high-level overview.
Thank you very much. Thank you very much for that introduction. Are there any hot questions for Tom? If not, I've got one. You've talked about re- reliability, high reliability, but when it comes to planning a network, if we want to address high reliability, we run into a risk of compromising the economical feasibility of the network. How can we strike a balance in the planning stage?
Excellent question. So the simplest way to provide reliability is, or sorry, redundancy, is just to have two of everything. Well, that is not cost effective. So especially with the remote units. So that's where the real system cost comes in heavy when you look at the overall bill of materials cost. The remote units are, each one is typically much more expensive than the head-end product. So this was an example of a redundancy system which was designed to strike the balance between performance and cost. So again, having the intelligence in the remote unit and having fiber diversity back to two head-end systems, repeating the cost of the head-end is relatively inexpensive compared to the project cost. So in this case, you don't need to you don't need to double up on the number of remote units. And there's different ways you can layer that in as well. You can have redundant RF modules inside the remote unit if you want to. But again, this particular system topology uses dual fiber feed with the intelligence at the remote to decide under what circumstance to hand over. And again, these can be large, complex systems with dozens or hundreds of remote units with a couple or several secondary head-end sites. Another way to do it is a different type of architecture, which we use in some subway projects, which is like a ring topology, in which case you can steer both directions all the way around. So if anything is cut anywhere, the system stays up. So from the planning standpoint, it depends on fulfilling a requirement. And sometimes the requirements are specified in the contract that they use the word redundant. Sometimes they just use metrics like reliability and availability, giving you 5 nines, which means you need to eliminate, single points of failure or multiple failures. So there is a balance to strike, and this is an example of how we've successfully done that.
Absolutely. I think you touched a really good point. It's not about duplicating the solution. The idea is to understand the requirements of the customer and creating the optimal architecture in order to guarantee the high reliability.
Exactly.
Thank you very much. And the last of our panelists, but definitely not least, is Francois Goudeneuve. Sorry for butchering your surname. He is the sales director at Syntony. He started on the engineering side in aviation, but similar to our first panelist, also moved to the commercial side. And he's specializing in location services.
Thank you. Sorry. Okay, thank you very much. The subject for this panel is critical communication broadband. Broadband is about data. Mm-hmm. And when you provide data, you expect much efficiency. And most of the time, the efficiency comes with the good location and the good timing. Mm. And that's what I'm talking about. If I find the right button. Just a few words about my company. We come from the space. In fact, not exactly space. We come from Toulouse, and we work for the space industry and the aeronautics industry. I've been working for many years as a GPS engineer for aircraft aviation. And our activity is to make GPS work everywhere. And that's basically what we talk about today. We have developed different types of services and products. We developed simulators to simulate GPS signals, and we provide receivers to get the GPS signals and to compute the position. Mm-hmm. As far as GPS simulation is concerned, the industry has seen this simulation move towards what we called software-defined radio. And it's very much more affordable than it was before. You can get GPS simulation for lower cost. And the Metro of Stockholm, they came to us and they said, we need GPS coverage in a metro for critical communication related applications. Could you help us to provide GPS underground? And that's why we jumped from the space to the underground. And that's basically what we do today. We have developed a service, a system that you can connect to the existing radio infrastructure, the leaky feeders, for those who are familiar with that, and the GPS signals will be broadcasted along the leaky feeders. So it means wherever you are in the tunnel, you can get your location. And you can get time synchronization, GPS-based time synchronization. And that's, I think, a very important step forward, because if you want to be efficient with data, you need to know where the data are, you need to know where the people are, you need to know what time it is, and how synchronized all those things are together. And that's what we have been working on. Very, very basically, how does it work? As I said, we can simulate the GPS signals that you would receive if there was not a roof above our head, and we will inject those simulations inside the leaky feeders. And then all along the cable, you will get a GPS position. In reality, it's a little bit more difficult than that. It's a little bit more complex. I have no time to go in the detail, but if you are interested, we can talk about it after all. The key issue is we can connect our system to an existing infrastructure. So you just have to put the simulation on top of an existing radio coverage, and then you get a standard signals. GPS, I say GPS, but it can be GPS, Galileo, Beidou, GLONASS, whatever. Today, mostly GPS and Galileo in Europe. And then you can get, you can get your positions. You can get everything that works with GPS will continue working underground. And that was one of the key issues for Stockholm Metro. They wanted the people to have the completely seamless transition. When they come from the outside, they should go inside the metro and get the same signals. The basic idea for them was to optimize the efficiency of the teams, and so they wanted to reallocate in real time the people depending on what's going on. So they can reallocate the people all over the city with all the transportation systems, except in the metro, because they don't know where they are when they are underground. So we just provided GPS coverage, and all of a sudden, the system became efficient 100% of the space, where it was not efficient inside the metro. And today, I put some elements here. The basic message is, it is not indoor location. It is GPS coverage. So no better, no worse. It works the same way. With GPS, if you have a good receiver, you can be very precise. If you have just a standard smartphone, you will get a GPS position which is more or less the one you have outside. But we can go very precise. And today, we have been working in very different types of environment. Road tunnels, metro environment, parkings, underground, but also mines. And every time we started with safety-related application, critical-related application. I believe it is because the people who better understand the radio infrastructure are the people who work on the critical applications. But once you get the GPS, it is available for anyone. It is available for any kind of application. And even if you don't ask for GPS for a given application, once it is here, you can use it. For example, if you want to have an information which is contextual depending on when you are in a tunnel to act on a given asset or do something different, it becomes feasible. Not because of this is not the reason why they will ask for GPS, but because GPS is available, it's just like outside. You have the feeling it's free. And that's exactly what we do provide today. And we are also working in more and more in an environment for autonomous vehicles. It can be autonomous vehicles on the roads, connected vehicles for the road tunnels or for the parkings, but it is also autonomous vehicles for mine operation, for example, or for industry activities like logistics or everything like this. But most often, as I said, the first step was to come from critical system for safety. I think I'm at the end of the short presentation. Just a last thing is we are working on standardizing this technology because it cannot stay a proprietary one. So it is standardized, and we are working with 3GPP and 5G working groups to make sure that it can be used by any kind of applications. Thank you.
Well, thank you very much. You took my last question there, which was how do we move this to an open standard and get in beyond a proprietary solution? And I believe you answered already by working with the standardization bodies. Do you have a timeline on the roadmap for?
Yeah, for the standardization, there are two things. The first thing is we use GPS signals. So as it is already standard. So if you want to get the GPS and only the GPS, it's working. I can tell you when you start the system, your GPS system will work. You need to get the right map. That's it. But it works. If you want to get a more precise position, just like you would like to make an aircraft land precisely, you need differential GPS or you need RTK. Those kind of augmentation techniques needs to be standardized as well. So that's what we are working on in the 5G AA working group. And the timeline is we hope to get a standard at least available next year. But after that, it has to go through all the panels and standardization work. And you know better than me, it's a long process.
Step by step.
At least the engineers will do their job for next year. Yeah.
Absolutely. Any questions? I do have one more question. One more question. We've covered the network planning of future, and we've touched two important topics. The coverage, how do we guarantee indoor, outdoor, a homogeneous service or coverage from our legacy technology with the new adopted technology. But my question to both Anthony and Tom is how do we address the capacity challenges? Is modular planning a solution? What's the answer from a planning perspective to the stage adoption of the technologies not all going to happen at the same time?
Yeah, so if we're looking at capacity, I think, we all use smartphones as we speak at the moment, so we're all used to sort of understanding what people can use those devices for. I think if we're looking at it in a sort of public safety type of environment, be it industrial or, government, then the devices we're going to be using are going to be sort of body cameras, tablets and those sort of things. Once we understand what they are, then it's very simple to simulate, either you can go out and actually walk around and just walk around, do a walk test with devices to simulate what capacity you're really going to use, or you can simulate it. But I suppose the one thing we're always aware of is that as people use data, they're always going to use more data and more data and more data. So we are data hungry. So whatever we're doing from the point of view of designing and planning systems, we've got to allow capability within the networks to overlay and add more capacity as it comes along. We're never going to sit still. And, if we go back to 2G, we couldn't do anything from data. Then we had 3G and we started doing stuff, and now we're looking at 5G where we can speed up and download stuff. And going off on a slight tangent, obviously that latency and the amount of data we're consuming also then migrates yourself into a little bit of the private wireless industry, which actually has synergies with this one, where we're looking at people migrating originally from push-to-talk to data-centric networks as well.
I'll just add one more comment to that. At the physical layer, I mean, it's not just that it's capacity. You're working with higher frequency bands, which obviously have different characteristics for propagation and penetration. And also you're looking at things for capacity like MIMO. So looking at some of the things we were talking about earlier, distributed antenna system architecture. For MIMO, for example, in a rail tunnel for metro, you'd be looking at two radiating cables, things like that, and very specially tuned and designed components. So you've got a combination of just the RF physics integrating with buildings, and just the again, it's not just capacity, which is at the user electronic level and data. It's also the physical level has to be properly planned out.
Absolutely. Thank you very much. So if there are no more questions, please join me in a big round of applause for our experts. Thank you very much. And I hope it's clear that we have to address the coverage differences, the intrinsic physical differences between legacy and the new adoption of broadband. We need to address the capacity and take into account the future demand. And also we need to account the needs that are going to come with a data-driven network with location-based services. Thank you very much. Have a great day.